This is the 16th and final episode in a series about designing and building a clock for my relay computer. Last time I constructed and tested the clock card, so all that remains now is to install it into the computer, wire out the Halt command and give everything one last test. Before I do though, let's pause to look back at what a mammoth journey this has all been. It started all the way back in episodes 1 and 2, where I covered why I need a clock, what a clock does, and some of the options for implementing one. I decided that I wanted something authentic, the relay-based clock, and something flexible, the crystal-based clock. I focused first on the relay-based clock, and it took episodes 3 through to 6 to get the basic design in place, and then in episode 7 I prototyped the design on a breadboard. With that in place, I could then consider the clock control design in episode 8 and get that all prototyped in episode 9. With the relay clock design in hand, I then focused on the crystal clock, getting the design sorted in episode 10 and prototyped in episode 11. At this point, I now had my 2 working clock prototypes complete, so it was time to draw out the schematic. A big enough task to cover a further 2 episodes. And then I could design the PCB based on that schematic. As soon as the PCBs arrived from China, I cracked on with construction and testing, which brings us right up to this final episode. If you've been following throughout the series, you'll know things didn't always go to plan, and I intentionally left all the mistakes, mishaps and learnings in the video so you can see what really goes on behind the scenes of designing and building a hobby project like this. Needless to say, mishaps happen all the time, but actually, one of the satisfying things in building a computer made of relays is finding solutions to the unexpected problems and learning as you go. Anyhow, for this clock card series, we're at journey's end, and so, for the last time, let's crack on. So here's the clock card in all its glory, and installing the computer is pretty straightforward. And actually there's only one free slot left over in the top right X-Bay. The card slides straight in, and then it's just pressed home, connecting it into the backplane. I'll make a legend plate for the card of course, and I create these in easy EDA just like any other PCB design. In this case though, I send them over to my laser printer and then laminate and stick them to one of my 3D printed legend strips. I'll do that some other time, but in any case, it'll look like this. With the card installed, I can now test controlling it via the computer primary switches. At this point it will just be the basic clock running and freezing, but let's start there. With the run stop switch here in the stop position, the freeze line is activated. And that means that although the clock is powered on and set to the crystal clock option, it's unable to run. That's exactly as wanted and means my first test has passed. Whilst in this stop position, all the other primary switches are active, along with the debug switches in display A here. When in run mode, all of these are disabled and the computer takes over operating the control lines. Let's flick to the run mode, and all being well, the clock will start. Brilliant. Okay, let's try changing the crystal clock frequency. Looking good. Let's stop, and that activates the freeze line again and the clock stops. If I set to run again, but flick the clock power, that stops the clock as you'd expect. Power back on and the clock starts up again. So the crystal clock is looking good. How about the relay-based clock? Yep, I'm very happy that's all working as it should. Marvellous. So you may be wondering why the clock isn't doing much even though the clock is running away merrily. Well, the clock drives the sequencer here, and the sequencer drives the controller here. However, when the computer is first switched on, the sequencer has no current state. We need to prime it into the first state, and that can be done with the reset switch like so. You can now see the LED lit here, which is showing the sequencer in the first state. Things get a lot more interesting now when we flick into the run mode. And you can see the sequencer stepping through its states here. I haven't actually entered a program into memory here by the way, it's just taking the random values in memory and trying to operate them. Anyhow, let's see how fast this thing can go. Impressively, the computer is still operating fine even at the maximum 32Hz speed. I'm not sure I'm comfortable running it that hard for too long, but still, impressive anyway. Now we're running at the slowest quarter of a hertz, and this is perfect for showing how stopping and freezing the clock only takes effect when the clock has reached the next off state. Cool. So that's all looking good. So how do we go about getting the computer to stop the clock itself? Well, we need a halt instruction. And here it is. Like all instructions for this computer, it's represented by an 8-bit opcode. And for halt, it starts with 10, 10, 111. The last bit gives us two options. When set to 0, the computer will halt, and that's it. The program counter in this case will be pointing at the next instruction in memory. Setting the last bit to 1 though allows the program counter to be set to a specific location in memory. That could be achieved of course by having a jump instruction straight after the halt, but this hardware option is available too. With the last bit set to 1, the program counter is loaded with a value set on the primary switches here. There's a catch here though. The address bus is 16-bit, and so is the program counter. But we've only got 8 switches here. Well, what will happen is whatever is on the switches will go into the lower 8 bits of the address bus, and the upper 8 bits will be cleared. Effectively that means you can only jump to somewhere in the first 255 memory locations. In theory, this could be used to allow a user to select a location in memory to continue from, but in reality, it'll probably not get much use, and it'll be the straight halt that I'll demo in this video. At the moment, the controller card is responsible for activating the clock halt line at the right time. However, it's not actually got the relays in for this function currently. That can mean only one thing. Yep, out comes the controller card. This is another of the newer cards that uses a professionally manufactured PCB, but you can see here where there's gaps for additional relays. On this upper card, there's the increment XY instruction class, along with the store and load to look forward to. This time though, it's the lower card I'm interested in, which means I'll need to split the two controller cards apart. This needs to be done carefully as there's quite a lot of interconnects between the cards, but with a bit of persistence, and there we go. Let's take a closer look at that lower card. So here it's the Move 8, Move 16 and MISC instruction classes we're interested in. The Move 8 is mostly implemented, allowing values in the A, B, C and D 8-bit registers to be copied. The missing registers here add registers M1, M2, X and Y to that list. Over to the right, the Move 16 class allows values to be copied between the 16-bit M, X, Y and J registers, and that's the majority of the missing relays here. However, it's the one down here that's of particular interest, and that fires the halt line based on the halt instruction that comes under the MISC class of instructions. So, missing relays, eh? Well, I'm sure you know what's coming next then. Now, I could just solder in the relays necessary for the halt instruction, but I decided that actually I might as well do all the remaining relays, meaning this card will then be complete and I can leave it alone. I'll not demo the Move 8 and Move 16 instructions in this video, but rest assured they'll work fine, and I'll cover a bit more detail on how they work on my blog at relaycomputer.co.uk. Likewise, I'll cover exactly how the halt instruction timing works and exactly what the controller is actually doing also on my blog in the next couple of weeks. Actually, I'll put a bit more focus on the blog for the next month or so, as I've got quite a bit of catching up to do. I'll update it for the new completed clock card, but I've also got a series of posts to do on the additional instructions I'm enabling here, and I've got a series of posts on how I made the assembler for my computer, which you can have a play with at editor.relaycomputer.co.uk. If you do make a program for my computer, then don't forget you can also try it on my simulator at simulator.relaycomputer.co.uk. Finally, if you do have a program you'd like to see my computer run, either something you've actually written or even just an idea, do let me know in the comments and I'll consider it for a future video. Anyhow, that's enough soldering. Let's fast forward. And here we are back at the computer, and the controller card is back in. We're powered up and we're ready to test that halt function. I'll put in the halt opcode and load that into the current memory location. Note I used the deposit switch there rather than the deposit next, so that the program counter wasn't moved on and it's still at location 0, as you can see here. Because I've powered on, I need to prime the sequencer, and then I can set the computer running. And very quickly the computer loaded up the halt instruction and recognised it as belonging to the MISC class, which you can see shown in display B here. With the instruction loaded, the sequencer advanced, leading the controller to activate the halt line, which caused the clock to halt. To make it clear to the user what's going on, the halt indicator is lit in display B here. So, now we're in the halt state, how do we get out of it? Well, this is where the restart switch comes in, which will release the halt latch and let the computer run on. Interestingly here, the random values in memory represent a goto instruction, which takes the program counter back to memory location 0, which is where our halt instruction is currently residing. As such, the computer picks up that instruction and goes back to the halt state. Restarting goes through the cycle again. It's pretty obvious now when the computer has reached the halt state, given everything falls silent. But I've got another trick up my sleeve to make it even more obvious. You might remember it from the end of my last video. Let's try it again now I've enabled this new feature off camera. There we go, the computer's much more assertive that it's finished a task now. Cool. The bell is a bit of a kludge at the moment, but I'll make it more permanent later. In case you're curious, here's what's happening. So that's it. The journey is complete and my computer now has its clock. Thank you so much to everyone who's been watching closely following this series, and an even bigger thanks to those who have been commenting and making suggestions and asking questions. These videos do take a lot of effort to put together, but if they're bringing enjoyment to even a handful of people, then they're worth the effort. There's still a load more I need to do on this computer, and I'll focus next on getting its instruction set complete, but after that there's loads of scope for fancy ways of loading programs into memory, or for having more interesting display and output devices. But anyhow, that's for later, and for now, thank you all for watching, and I'll see you next time.